Classical Cauchy Schwarz inequality in different form. So in angled forms, if you rewrite this in terms of components of a vector, so you'll get the following inequality. So this is the classical inequality that everybody uses, and at some point people started looking at this inequality from different perspective, and this perspective makes a lot of problems, a lot of contest math problems very simple. So if you rewrite the inequality in the following form, the sum of elements of the first vector squared divided by the sum of elements of second vector is less or equal to less than this quantity. So this doesn't look like Cauchy Schwarz inequality, but if you properly rearrange the orders, you will get the Cauchy Schwarz inequality. In order to prove, I'll just give you the idea of the case when n is equal to 3. Then you can generalize this for n equal to any number. And we will use this case, probably the most common case when n is equal to 2, to solve several problems, examples. So let's go to the problem when n is equal to 3. So when n is equal to 3, the inequality becomes, I'm going to write the larger side on the right, on the left. So it's going to be for positive integers, positive real numbers. A squared over x plus b squared y. So square of a number divided by some real number. That's always greater than or equal to. What's very interesting about this problem is you can just sum the top. So that makes a plus b plus c squared. And then on the bottom, you just get the sum of numbers, x plus y plus c. X plus y plus z. So that's the case when n is equal to 3. So if I rewrite this equation in the following form, so let me rewrite it like this, and then you can see how it's a Cauchy Schwarz inequality. If I do square root of x squared plus square root of y squared plus square root of z squared. So that's my first vector. And then the second one, if I do a over square root of x squared. So basically this is a squared over x. So I'm rewriting it in a different form. Same way b. And then we get the c as well. So that should be greater. So the length of first vector, the squares of components of the first vector by squares of components of the second vector. If you do the component-wise product, you will get on the other side. So let me put it here. That would be square root of x multiplied by a over square root of x. So on the left, you should get a plus b plus c squared. So if you take this parenthesis and then divide both sides by x plus y plus c, you will get the Cauchy Schwarz in this form. So that's basically the proof. So you can generalize this for any number, n is equal to any number, and then you can use it in a different form. So now the question is how this makes our problems easier. So let's take a look at some problems from past math contests. So the first one is going to be the following problem. although this is problem from some small contest, I would say. I don't know which one, but this is also a contest problem. So if you rewrite this equation in the following form, so if you divide both numerator and denominator by 2, you will get 1 over x plus y over 2, right? So 1 is a square of 1, so it's okay to write as 1 square. The same way, 1 square over y plus c over 2. And then here we have 1 square z plus x over 2. Now recall the inequality that we had, the Cauchy Schwarz, in a different form. So we have squares of 3 numbers on the denominators, on the numerators. So on the top we expect, so this would be using that inequality, this would be 1 plus 1 plus 1 squared. On the bottom is just sum of these 3. Since this is a halves of x plus y plus z, so when you add these 3 numbers, you just get x plus y plus z. And then this one is 9. Okay, simply rewriting this equation in the following form, you can state that this is a Cauchy Schwarz inequality, and that proves your problem. So next one is it's a very old problem from Asian Pacific Math Olympiads. This is an international Olympiad, and we have two set of numbers, A1, A2, AN, and B1, B2, BN, where the sum of numbers is same, and we want to prove the following. So this is a straightforward Cauchy Schwarz inequality in the above given form, because if you look at this left hand side of the equation, we can immediately say that this is the squares of the numbers on the top, so that's greater than the sum of squares, square of the sum, so a1 to an, and in the denominator we get the sum of all numbers, so that's going to be sum of all numbers ai and bi. So sum of numbers a and b, since they are equal to each other, I can just remove this and then write it as 2 times ai's, right? But as you can see, we have the sum of numbers here and the square of that number, so you can cancel out this and this, so in the end you are left with 1 over 2 and just the sum of numbers from a1 to an. So applying the Cauchy Schwarz inequality here, straightforward, gives you like 2-line proof of a problem that comes from an international problem, the International Math Olympiad actually. Another problem that's a very old inequality. It used to be difficult at a time, and then there are different ways to approach this problem, and one of them is using Cauchy Schwarz. Here, since we don't have squares, I can just multiply both. I can get the square artificially by multiplying by a, right? So I can write a square. On the bottom I have ab plus ac, and then here second one is going to be I will multiply with bc plus ba, and then the last one is c square is ca plus cb. That's greater than 3 over 2. So this is what I'm going to prove. So since now I have the squares, so the left hand side is going to be, so the left hand side of the equation is So let's forget about this for now. That's greater than a plus b plus c square, and that's divided by the sum of the numbers on the denominators. That's going to be 2 times ab plus bc plus ca. And that's easily greater than 3 over 2. That's easily greater than 3 over 2, because, so ignore these 2's, they are common, and then you can see that a plus b plus c square is greater than 3 times ab, bc, ca. This is just like when you open the parentheses, that's square of 3 numbers is greater than the pairwise products. That's simple. This one is a simple one. You can pause and try to finish the problem from here. And then the next one, this is 1999 from Czechoslovakia. Again, it's a very similar problem. I would say it's almost same. You do the same trick, and then when you do the same trick, you get a square ab plus 2ac b square bc plus 2ab and c square ca plus 2cb is greater than, on the top numerator becomes a plus b plus c square greater than 3 times ab bc ac, and that comes to the problem, the previous problem again. That's greater than or equal to 1. So if you prove the inequality in the previous problem, then you are good with this one as well. So this one is a tough one, but again, you can get some equations from using the following. So I'm going to take, so this is a cube, I'm going to take this square of it to the numerator and rewrite the equation as, the expression as the following. So it becomes a, it's similar to the previous 2 problems basically, and then 1 over b square over b times a plus c, 1 over c square c times a plus b. Now this equation using the Cauchy Schwarz, it's going to be greater than the sums of inverses of these 3 numbers. So 1 over b, 1 over c square. On the bottom we have twice ab plus bc plus ca. So these 2 expressions are equal to each other, so you can easily verify that ab plus bc plus ca is equal to 1 over a plus 1 over b 1 over c. So if you do the common denominator, because we are going to use the following identity, ab plus c, they are equal. So basically this expression boils down to, so I will just cancel one of these, and then I write as a b plus bc plus c a over 2. And then if you apply the inequality between arithmetic mean and geometric mean, you can get that this one is greater than 3 times the cube of the product ab bc ca over 2. And then this sum under the square cubic root is going to be 1 again, since abc is 1, that's 3 over 2. So very simple perspective, a different perspective, rewriting the Cauchy Schwarz inequality that makes a bunch of previously difficult problems very easy. So it's a very small, very classical problem. If it's a international math Olympiad problem, it doesn't matter. So the perspective, a different perspective, makes whole bunch of difficult math problems very easy.